So hi everyone, and welcome to the last lecture, or at least the last of the conventional lectures. We will have a guest lecture after Easter. Dr. Kieran Hughes from Vallejo Vision Systems is going to give us a lecture on the probably on that Tuesday in the normal slot, unless something changes in the meantime, which I'll let you know if it does. So this will be the last of the conventional lectures that we're going to go through, and it's on bundle adjustment, which is an idea that comes. I'll mention this again in a minute, but it's an idea that comes from photogrammetry. So that idea of measuring things in photographs, which kind of separated off as a separate research community from computer vision quite a number of decades ago, and is now kind of the two have probably more in common now than they had for a long time. But they would have been looking at this rather than the computer vision community. But it's basically an idea that goes a little bit beyond what we looked at up until now, which was the idea of just having a closed form solution to trying to solve our camera motion and the structure of the 3D scene, which is what most of the courses or this module has been about. So we're going to go a little beyond that. So the idea here is that we're going to look at computational projective reconstruction. So using computational means here rather than using pure mathematical means that you could almost do by hand. Okay, so this idea is just using computational means, which tends to be not as elegant or neat as the mathematical methods. So previously we looked at analytical methods of computing structure and motion. However, we noted that while they were neat mathematical solutions, and they were often quite efficient as well, they had significant problems in the presence of noise. So by noise here, what I'm referring to is anything that can interfere with our measurements. So it's important to kind of always get an idea of what we mean by noise, what type of noise we're dealing with and what effect that it's going to have. So we're used to thinking about maybe noise in terms of audible noise, and you all know what that sounds like. In fact, I've got a fan on here behind me, which I'm going to switch off. So I don't know whether you could hear that or not, but it doesn't matter. I could hear it certainly. So that would be an example of noise in the audio sense of things, and we've obviously lots of other examples of that. Within images, though, we tend to think of noise as how it's going to affect the brightness values of our pixels. So you think of it as the grain that you used to see on the old terrestrial television, and you can kind of see that if any of you take images at night or in the darkness with your mobile phone cameras or that, you see a lot of noise in there. Okay, so that's the type of noise you tend to think of. But in this particular case, what we're referring to is the effect that this has on our measurements of where a 3D point appears within a frame. So where we would ideally like it to appear, in other words, if it appeared perfectly, versus where the pixel that it actually appears at, which may be some number of pixels in some direction away from the point where the point should actually be. Okay, so that's what we mean by noise in this case. So it's something that causes our points to not appear exactly where they are. Now the problem with that is that if we've got lots of frames and we've got corresponding pixels that we've found, or corresponding features that we've found within those images, but those features are not exactly placed where they should be, then that makes it difficult for us to then try and reconstruct the scene, and also to reconstruct the camera motion that has taken place between those two. Okay, and of course, if it affects all the different features in all different ways, then it's kind of a random process, and we need to kind of think of it like that. Okay, so what we'll now look at are computational means for estimating the structure and motion. They're not neat generally, and often they're inefficient. In fact, in some cases, it's very difficult to even determine exactly how long they are going to take to do. So that can be quite problematic, particularly in systems where you require a deterministic response. And by deterministic, I mean that we're able to determine how quickly something will happen. So in a situation whereby you're trying to make a decision within a certain number of microseconds, and you know something about your hardware performance and so on, you also need to know something about your algorithm and how quickly it's going to take. And if that varies depending on the problem, then that's not just a problem in terms of it might take too long. It's a problem in terms of we don't know how long it's going to take, and therefore it's more difficult to trust. So they're often not inefficient means, but they can give us a better result. So if you're in a situation where you have all the time in the world, or at least you have a lot of time and you've got heavy computing power, then you can throw the most inefficient algorithm at it if it's going to give you a better response, it's going to give you a better reconstruction, and that's okay. But in situations where you're dealing with an embedded system on something like an autonomous vehicle, which has to make decisions within a certain number of microseconds in order to keep everybody safe, then in many cases a lot of these algorithms get ruled out, and even though they might give you a better result, you have to make that trade-off. And so that's something to kind of keep in mind if you ever get deep into some of these methods. So these will rely on non-linear methods. So when we talk about linear methods, those are methods that we can quite easily compute analytically, and they'll have what we call a closed form result or from that. So that basically means that we can just calculate a result, and that's the end of the story. With these, we generally have to kind of find our way to the result in some sort of iterative manner, and therefore it can sometimes be difficult to tell exactly how long that's going to take and what's involved. So this term bundle adjustment, as I said, is a term that came from the field of photogrammetry. But again, you know, most of what we've done here is a type of photogrammetry in that we're not necessarily trying to do measurements yet, but we are trying to at least tell where are 3D points within a space. And the whole point of doing that would be that you might want to measure how far something is away or try and reconstruct it, which of course would require measurement. Now the idea here is that the term bundle refers to an entire bundle of rays. So if you think about a point in 3D space and you've got rays coming out of it at all different directions and so on, and those rays intersect with different camera views, and we considered all of those rays together, each of the different rays that all go from each of the camera views, so from the camera view center through the through the frame and up to that whatever that 3D point is, so from all your frames, them all together, they're considered, you know, a bundle. And of course, if we have multiple points and multiple views, we can bundle all of these together in one bundle, and so we're going to treat them all the same. And from that point of view, in other words, they all have to be as close to the result as possible for us to be happy. So we treat them all as a bundle rather than treating each one individually. Why is this different from what we've done previously? Well, if you consider the two-view case, what we would do is we would find we'd find the same feature in two frames, and what we would do is we would try and use that in order to determine, you know, via the 8-point algorithm or whatever, we try and determine our rotation and translation, and from that then try and determine the 3D point where they match. So we generally only be dealing with two rays and two views and one 3D point in order to try and calculate that. Now, of course, with the 8-point algorithm, we had 8 points, and we would try and minimize it to that point, so that each one of those would meet. But again, we're only maybe dealing with two views. We then looked at multi-view cases, and we said that actually any 3 views would be enough to find many things. So if we went looking for a line, for example, they would only have a consistent pre-image if all 3 of them lined up. But this is different here. We're taking often many more times a much higher number of these rays, and we're trying to get them all to match as closely as possible as we can in all the different views all together. That's quite a different scenario. So that's what we mean by the bundle, and the idea is that we're going to vary our rotation, our translation, and our 3D points settings until we get a setting that matches all of our correspondence points. Now, if you think that sentence just looks like, oh, okay, that's all we do, you haven't thought about it enough, because the problem is, you know, all the different rotations that you can possibly have, and all the different problems that are associated with that, all the different translations you could possibly have, and then all the different possible points you could have. And we don't know where the points are, so what we're going to do is we're going to guess some point, or we're going to guess a load of them, and we're going to think about how they project into each of the different camera views that we have. And we don't even know where the camera views are, because we don't know our rotation or our translations for each one of them. And what we're going to try and do is we're just going to try and tweak each of these as if we're like tweaking some small little knobs in order to try and get everything to line up. And the problem is you just have a vast dashboard of little knobs that you're going to try and be twisting, and very difficult to tell exactly what those settings should be. So this is a very, very difficult problem that we're suggesting here to try and solve, to try and you know, just modify each one of these in a small fashion. Then if we do, right, so let's say that we do, and the whole idea is that we're trying to line it up with these points that we have in our images, but if the points are noisy, won't we just line up with the wrong points? Okay, which is what most people would assume when we have this. And the answer to this is both yes and no. Okay, so firstly, the yes. There will be no rotation, translation, and points that we can pick that can possibly get the rays to all line up unless there is no noise. Okay, so in the presence of noise, there is no rotation, translation, and points that we can pick that will perfectly line them up with all of the noisy points. That may sound like a bad thing, but actually it turns out it can be quite a good thing. Okay, so the second part of this is because the noise should cause our image points to randomly be out by different amounts in different directions. This means that if we can find the bundle adjustment that gives the least error, then we're likely to have hit the center of all the noise. Which means that we're going to find rotations, translations, and remember there's going to be multiple rotations and multiple translations because we've got multiple images and we've got lots of points within those. And if we get this just right, that we get the minimum error from all of the points that we actually measured in our images, then what we're likely to do is that the points that we're likely to have found within the images are likely to be more correct than the ones that are actually measured in the images. Okay, so there's a clear difference there, and the reason that should work is because it's caused by random noise, and therefore it's randomly off in different directions. So Vin is asking, would this affect depth perception? So absolutely, right. So bear in mind that your rotation, your translation tells you how far different camera views are apart, and they're trying to see some 3D point. We're now guessing our rotation, our translation, and our 3D points. And what we're saying is, given our 3D points, if we take our guess for our rotation and our guess for our translation, where does that end up inside the frame? And then we measure the difference between that and where the actual point is in the frame, and we try and minimize that. So we try and minimize that by changing our rotation, changing our translation, and changing our 3D points. So we don't try and make a determination about what the depth perception is until we've minimized this, until we're fairly certain that we've got the correct rotation, the correct translation, and the correct 3D points. Once we've got that, we're as close to getting a reconstruction of the 3D world as we can get. The problem is finding the right one is the trouble. So our images will, you know, these things will be in the wrong points, but the thing is that if we get the minimum over all of these, the points that we guess them to be at should actually be more correct than the ones that were actually measured in the image. So so this means that we can find the bundle adjustment that gives the least error, then we are likely to have hit the center of all the noise. And the center of the noise is the point that is most likely to be the true point. Some terms and conditions apply to this. We need to look at those first. So this idea that the true value is at the center of the noise is based on an idea called the central limit theorem. And any of you that done digital signal processing with me, we done quite a bit about this. And if you were in third year DSP with me, you would have looked at the difference between accuracy and precision. So I don't know if any of you remember that, but you probably studied it for an exam at some point. And there is a difference between those two terms. But firstly, to make this work, it firstly assumes that the distribution of the noise is Gaussian. Okay. Now, this term Gaussian comes up again and again and again, and you've seen it throughout the course, and I'm sure you've seen it throughout your maths module as well, where you're dealing with statistics. This is not a bad assumption. In fact, if you know no information about something, there is no better assumption you can make than to assume it's Gaussian. There's just literally no other option you could take that would be right more often than the Gaussian. That doesn't mean that the Gaussian is right. It just means that there's nothing else that could possibly be right as often as picking a Gaussian for that. So it's not a bad assumption if you know nothing else. It secondly assumes that the noise is not biased, and I'm going to explain what I mean by that in 1 minute. But again, you've probably covered it in your applied statistics and probability. So bias is normally associated with calibration. So systematic errors. And normally speaking, we can deal with that by trying to calibrate our equipment in some way. That mightn't just be the lens, that could be all sorts of other things to do with the camera setup. But the point is that it's something that you have to solve with calibration. We're assuming that it's not biased, and therefore we're assuming that we've got our best calibration setup that we possibly can. If we don't, then there's nothing that we can do in the bundle adjustment that is actually going to counteract that, particularly if we don't know about it. And therefore, what that means is that whatever amount we are out, whatever amount we're biased by, the bundle adjustment will also be biased by that amount as well, our result, and therefore that is a problem to consider. However, if we can assume that the noise that occurs, in other words, that the incorrect or the errors within the points within our images when we reproject them, when we find those features in the images, that noise there, that is random and in a Gaussian manner. Okay. So thirdly, it assumes that we have an infinite number of measurements, which of course we don't. We only have a small number of them, and the more we have, the more measurements we have, the better our precision will be. Okay, so if we have a small number of measurements, we're a long way from infinity, and that means that we have a bit to go in terms of our precision. Okay, and those two terms, accuracy is to do with bias and is to do with calibration. Precision is to do with the number of readings that you've taken, and the more readings that you take in terms of precision, you can then be more sure about what the true value was. The problem is that the more measurements, the more computations, because if you keep in mind that the more measurements probably means you've got more frames, or you've probably got more 3D points. And between the two of those, they are going to add up to an awful lot more computations, because you've got lots more in your bundle that you're trying to adjust, and that makes things much more difficult. So maybe just to make sure that you're clear on the terms of bias and variance when it comes to Gaussian noise, I'm just going to give some examples here. So firstly, if we have low variance and no bias, so what I've picked here is a dartboard, and what we're assuming, any of you that know anything about darts will always kind of have an issue with the example, because the example we always do is we look at the bullseye. But if you know anything about darts, it's actually up here. This is the one that's actually worth more points, and this is what they normally aim at. But once again, we're going to be aiming at the bullseye, because this is what makes much more sense. We're not playing darts here. We're simply doing this. So let's imagine that we have a dart player and they're throwing at it, and they have no bias. And what that means is that there's nothing within the throw of their arm that's causing them to go in one direction. So I'll show you what happens when we bias at the moment. At the minute, they're just a little bit random. Okay, so we're assuming if they have low variance, they're a pretty good player. Okay, and what we're going to get is the majority of the points are going to be in the center, and then we've got less as we get further out. Okay, so this would be a Gaussian distribution around this, and it's all fairly close to the center. It has no bias associated with it, and if we add up or average all of these, what we should find is that we've got a point in the center, which is there, and that would tell us where the center of the bullseye was if we average all of these. Okay, so this is why I say that if we do our bundle adjustment, and of course our where we reproject them, where we think they should be in the images, doesn't exactly line up with the measurements that we've taken, but the measurements that we took we know were incorrect with some amount of random noise. And what this is going to tell us is that well, the pink ones there, the pink dots there are all the random noise. What was the true value? And it should all line up that the best result you get is the one that's based on the true value. That's the idea. Okay, so that's if we have low variance and no bias. If we have high variance, here is what we get. We still get a situation where we have mostly in the center, but what we start to get is we get a few more out the way. And of course, these are all supposed to be just dots. Okay, I'm not drawing them particularly well. And you can see that they're spread much more. Okay, now we don't have an infinite number of points here. And if you were to add up these, the chances are, just the same as the last case, by the way, as well, that because I don't have an infinite number of points, I may not be absolutely perfectly on the center. I might be somewhere slightly off. But if I got my darts player to play forever, I kept throwing at it and I kept measuring. This blue point would get closer and closer to the center the more points that I have. So again, the noise is all over the place, but in actual fact, because it's random and we've got lots of points, the answer we should get should be in the dead center. So what about low variance, but we do have some bias. So let's just, actually what I'll do is I'll just grab my, thing has disappeared here, I don't know why. There we go. So what I'm going to do is I'm just going to grab my low variance one here and copy it and move it over to the to this example here. Okay, so what happens in this case is that if we have some bias, and let's say that the bias is all in a particular direction, okay, so the bias is all up in this direction here, what's going to happen is when we take these points, I'll actually just get rid of my arrow, sorry there guys. So what we do is we take our points and they will all move in that direction there. Okay. Now the problem is that if we measure all of these points and we add them up and we get the average, we're gonna think that this blue point here in the middle is our true value. So if you have systematic errors such as calibration problems and so on, the chances are they're going to be biased in some way. Now it can happen that, you know, things like radial distortion and that over the entirety of the image may well have an effect somewhat similar to a Gaussian, and therefore they may counteract each other at different parts of the image. But in general, calibration problems are going to send you with a bias in some direction, and that's quite problematic because you're not going to find a result. So that means that your true value is going to be out by some amount. Okay, so that's low variance with bias. And what happens if we've high variance with bias? Well, pretty much exactly the same thing. So all that happens then is that we move in some direction, and we can move in any direction. It's really very difficult to know. It's not like we will always know what direction we're going to move in, because if we knew, we might be able to calibrate that problem out of it. Okay, so what I might do is just I'm just going to add one more to this, which is this, which I really should have put in here. So, oh dear God, I wrote height variance instead of high. So pretend that isn't there. Okay, and the same on this. We'll actually, what we'll do is we'll just cut out the whole of this, because this is I'm not showing the same thing here at all. Right. What happens now when we only have a small number of points? So let's say, for example, I get a point there, and I get a point here, I get a point here. Okay, so I've only got 3 points now. What can you tell? Well, where's the central point? The central point might be there somewhere. Maybe there, about there. Okay. But now let's say I get another point and it's here. Now my central point is going to move somewhere else. It's going to try and move to try and be maybe there somewhere in between them all. Okay. And then let's say I get another point, and that point is here. Okay. You can see how the different ways it's going to move. Now the thing is that if we only have a small number of points, it's very difficult to determine what was the Gaussian that actually meets with that. Okay, so you can see here the guess would be, after only 5 points, that we have some bias here in this particular example. Again, you're not going to know that you've bias or not, but we only know we've bias because we know that really this should be the true value, but you don't get a dartboard to look at. You're only trying to find the center. So you can see the sort of problem here when you've only got a small number of points, and actually you have to build up quite a number of points before you start to find exactly where the center is going to be. And once you do that, then you get a much better idea of it. Okay, so this is what I mean by trying to when you have lots of points, it's much easier to find your correct value. But the problem is, the more points you have, the more calculations you've got to do, and this all adds up. Okay. So just move this over. Actually, it's okay. So in our projective reconstruction, imagine we have a set of 3D points which we're going to call xj, where the j is basically going to represent each different point. Okay, and we view these with a set of camera views pi. So this is each of our different camera views. Now remember, p is going to include both the rotation and the translation. Okay, so it's going to include both of those. And I there just tells you which camera view we're looking at. Okay, so we're basically going to have an RI and a TI there as well. Okay, put a little dot on the top. So we'll denote small xij. So now remember, of course, these are not, as I know somebody asked before, is that to the power of I? And it's not. It's just a way of indexing two different things. So what we were looking at here is the position within a particular camera frame. So the I tells us which camera frame we're in, and the J tells us which of the 3D points this refers to. Okay, so we can have lots of these. So we'll denote xij as the coordinates of the jth point as seen from the ith camera. And we want to estimate the projection matrices. So this is our estimate, okay, with the little hat symbol on it. This is our estimate, and what we hope is that they are the actual real ones when we're finished. But to start off with, they're going to be clearly wrong. At the end, they're probably still going to be slightly wrong, unless we've done a very bad job, in which they might still be completely wrong. But that's why they have a little hat on the top of them to suggest that these are estimates. Okay, so we want to estimate the projection matrices P hat I and X hat I. And remember that there's going to be quite a number of these and quite a number of these, right? So what happens is that we project our 3D points that we think, so our guesses, and we project them into our guessed projection. And that tells us where within each frame, I and J, that's our guess is going to be. Okay, so this is our guess of where points should appear in frames. And what we're going to do is we're going to then compare that. So we just take the two of those, which is basically the same as just having the little x hat ij there. So that's that section there, and we compare it to the actual measured values, which, as we said before, are likely to be noisy and likely to be somewhat wrong. So what do? Well, we get the distance between the two of them. So this is just using the standard Euclidean distance, which you're familiar with. So basically what we do is we just square them and we sum them up. Okay. So normally what you do with the distance, when you're trying to find the distance between something, is that you get the square of them and then you get the square root in order to find the actual distance. It's the Pythagoras theorem. We normally don't bother with doing the square root of it here. We're just doing the squaring part. And the reason for that, I think I said it to you in previous lectures quite a bit of time back, is that when you're trying to find the minimum, you're trying to look for the derivative and then therefore find where the derivative is 0. And generally speaking, if you've got a squared component, that's actually a little bit simpler to do than to do it with without that. Okay, so it's not really that there's anything particularly special about that, but do bear in mind that as your distance goes up now, the penalization for that goes up by the square of that. So it actually penalizes outliers by much more. And that means if you have one point within your system that is a considerable outlier, that's going to put your error off by a long way, and it can mean that it introduces an error into your result that's more significant than it should be. Okay, so that is something to remember, and they can actually, of course, do them without the square as well if they want to. It's maybe a little bit more complex, but other than that, it is doable. So what they're trying to do is they're trying to sum up all of those errors. In other words, how far are we out? So all of our guesses, reproject them into the images, get the distance to all of the different points that we have, and bear in mind now that you're now asking the question, well, which point am I measuring the error from? Okay, and that again, that's something that can become a problem. And this is we'll come back to that in a moment about initialization, but so you can maybe just take the error to the closest one for the moment. And what you want to do is you want to sum all of that up. It'll probably end up coming to quite a big number, but what you want to do is you want to minimize that. Okay, So you want to get that down to its minimum. You're never going to get it to 0. The only way it could possibly get to 0 is if you had absolutely no noise. You're definitely going to have noise, so it's going to add to it. If your noise is high variance, like I showed, you're going to have quite a bit of an error even at your minimum. If it's low variance, you're going to have a small error, but the point is you're going to have an error. Okay. So that's the idea of what we're going to try and do. But bear in mind, we've set ourselves a very complicated task because there's loads of these points, loads of these rotation and translation matrices, and we're trying to guess them to start off with and then try and bring them slowly closer to what we want them to be. So the estimation involving minimizing the reprojection error is known as bundle adjustment. We adjust the bundle of rays between each camera center and the set of 3D points and try and get the result. So following in line with previous mention Father Ted, I have another example here. Are you familiar with this episode, folks? Have you all seen it? I'll explain it anyway in a moment, right? And what its relevance is to this, okay? Because I haven't just thrown in the joke for nothing, okay? So in this particular, in this episode, Ted has borrowed a car for reasons which I won't go into. I won't spoil it for anybody who hasn't watched it, but it has a dent in it and he needs to get that dent out of it. And so what he decides to do is that he's just going to get a little hammer and he's going to tap the dent out of it, rather than going to a professional. So in our example here, Ted is like the algorithm that we use for our minimization. Okay, Ted is like the algorithm that you try to use to get your best solution. And as you can see, Ted is not a good algorithm. Okay, so what happens, Ted, is that he sets off from actually a very good position where he only has a tiny little dent to remove. It goes slightly wrong. He tries to undo it. He tries to undo it again. He tries to undo it again. And a few hours later, he's left with this this car that we see at the bottom, which is an absolute wreck. Now, the thing here is that the algorithm that we're talking about, whatever algorithm we use for our minimization, that has to be good. But no matter how good it is, if we start from the situation that Ted has left the car in here, so imagine that you go to an expert panel beater who's our good algorithm, and you say, this is the car in this state, can you do anything about it? The person would say, as happens with a lot of Irish people when they're asked directions to somewhere, I wouldn't start from here. Okay, this is not a good starting point, and no matter how good the panel beater is, they are not going to be able to bring that car back to the situation that it should be. So this represents, this here represents a poor starting point. Whereas what Ted started with just a small little dent, that's a good starting point if you've got the right professional to actually solve the problem. So for us, this means that it really doesn't matter how good our algorithm is. If we start with something like this in terms of our algorithm, then we're unlikely to ever solve the problem. And the problem is pretty much as big as what we're seeing here. Okay, we've got so many 3D points, so many camera views that, and we've got all those problems with the rotation matrix having to have all the properties that it's supposed to have, that the chances of us finding the actual solution are actually very slim unless we start from a pretty good position. If we're in a pretty good position, then we can get there, but if we're not, we're in trouble. Okay, so both the initialization, our starting position, and the algorithm have to be good in order to actually get us there. So obviously, again, if we start from a good position but we've got a very poor algorithm, then we've the same problem as Ted had. It's probably still better than the Father Jack algorithm. There's no doubt about that. Exactly. Okay, so firstly, so this comes out. So where do we start with the values with our guesses for these? So where do we start with our guesses for these things here? Because that will then determine what our starting position is. So unless you have better ways, so for example, some prior knowledge of the scene, what you should do is you should start with the techniques we used earlier in the module. So you could use the 8-point algorithm to help you do the multi-view methods and get yourself as close as possible. So this only requires tweaking. So you may remember that we said, okay, the 8-point algorithm, that's going to get you some reasonable indicator of what the 3D point and the rotations might be, but it won't be perfect because there's noise. And then we talked about, well, if you've got multiple views, you can extend that. So it's sometimes a good idea to start with the 8-point algorithm, then iterate to the other, to other algorithms, back and forth, and try and improve that. So what you could do is you could start with the 8-point algorithm with just 2 views, get a fairly good idea of all your 3D points, because all your 3D points should hopefully appear in all those. then you have this, the situation of trying to improve that maybe with the multiple views, and when you're in that position, that's a good starting point for this algorithm then to finish it off or polish it off. So you've pretty much got your car in your good state there, and all you've got is a few little dents to knock out of it with a properly good algorithm. So one of the things that often happens is that you cover a certain amount in a module, and you say that there's all the problems, and people assume then that when you show them this better algorithm, that what's going to happen is that they're going to ignore those previous ones. We don't tell you those for nothing. They're still useful. They're the point that gets us most of the way there. We get a little bit further maybe with the multiple views, and then we can polish it off with these methods here. There's one point that just popped into my head there, and I don't know if I mentioned it here. When is that the J? Yeah, I can't remember, is it here or somewhere else that I mentioned. Just one thing to be aware of is that I think it's actually, sorry, I think it's in a few slides time, but just in case I forget to mention it, is that from our multiple views, every point may not appear in every view, okay? And that's something to kind of keep in mind. So what that would basically mean is that you clearly would not want to include, yeah, sorry, it is here. It's for every view in which the 3D point appears. That was the line I was looking for. So it is important to remember that sometimes you might have some sort of an indicator function here that says, did this point appear in this view? Because if it didn't, then you've got a huge distance, and you shouldn't include that in your bundle adjustment. So it's perfectly reasonable to leave some points out if they don't appear in a view, but include them for the views that they do appear in. Okay. So this brings us on to the dimensionality of the problem. So normally when we talk about minimizing something, you know, we draw, and I'll be even drawing some of these for you later, we draw some sort of curve or whatever, and we're trying to find maybe the minimum of the curve like that. But this is a one-dimensional curve, and the problem is that what we're talking about here is much larger problem with much larger number of dimensions. So each camera view has 11 degrees of freedom. We've seen that previously, and each 3D vector has 3 degrees of freedom. So a reconstruction of n points over m views requires minimization over 3n plus 11m parameters. So if you consider that we've, let's say, got 20 points that appear in all 5 of our views, okay, let's say, then what that's going to mean is that you've got 30. Have I that right? 3n. Sorry, I haven't it right. That's meant to be 60. Because the number of points, sorry, that should be 60. I didn't notice that today when I was going through it. So 60 plus 55, so it's going to be more than 85 dimensions. It's going to be, what is that? It's going to be 115 dimensions. Okay. If that's the situation, then we're going to have that number of dimensions. So I want you to imagine, okay, you're used to 3 dimensions, and you can maybe kind of comprehend maybe what 4 dimensions is like. Now you've got 115 dimensions, so that's 115 axes to deal with, and you've got some kind of surface in that, okay, but it's a 115 dimensional surface that's in it, and you're trying to find a minimum point in it, okay. It's usually best not to think about that. The human brain is used to seeing things in a 3-dimensional world, and when we try to envision things beyond that, it's generally not useful for us to do so. We normally think of things in kind of 2 dimensions or 3 dimensions, or maybe only 1 dimension, so we can visualize it. But the mathematics has no problem doing it. It's just that the problem becomes much bigger. So there are lots of these algorithms for solving these, but I mean, some of these, and of course my 85 is wrong there, it should be 115 by 115, but to be honest, both are a big problem. If you have a matrix that's that big, 115 by 115, and you have to start kind of factorizing it or trying to invert it. So imagine I give you a sheet of paper, and I give you a 115 by 115 matrix and say, give me the inverse of it. You've got a big problem on your hands. You're going to be here for the rest of the year doing that on paper, and even with a computer, it's going to be slow. There's a lot of calculations involved in it. So you can see how as m and m increase, so if we have more points and more views, this becomes very costly, and for very dense reconstructions would become essentially impossible. Oh, and there's that extra little problem, of course, that the OR matrix has to have all those properties that we discussed. So generally speaking, what you're going to have to do is you're going to have to go into that Lie space that I told you about, and then try and use that exponential map with the Rodriguez formula to try and bring yourself back to the rotation that you want. But the dimensionality problem, firstly, how do we go about, what are the solutions around that problem? So the first thing you can do is you can just reduce n or m, or both. You can do a thing called interleaving, we'll talk about in a second, or we can use sparse methods. So we'll just talk about each of the three of those. So what you can do is you can leave some points out or some views out. And you can fill them in later by triangulation or resectioning, respectively, for the different things that you want to do. You could also partition the data into several sets, bundle adjust each and separate and separately then. So bundle adjust each of them separately, so you're dealing with a smaller bundle, and then merge them. Try and merge them in some way. So you can have a look at the Hartley and Zisserman book if you ever come across this and you want to go through it in more detail. They come up with a much larger discussion on that method in section 8.6. Interleaving then, basically what this does is it alternately, firstly, minimizes the reprojection error by varying the cameras only. So only varying the rotation and translation. Then what it does is it minimizes the reprojection error by varying the points only, and it goes back to the other one and back to the other one, and you should get closer and closer as you go. The reason that this is useful is that because you're not doing the two together, the dimensionality of your problem drops. So the advantage here is dimensionality. Each point is estimated independently given fixed cameras, and similarly each camera is estimated independently using fixed points. So the largest matrix then you have to deal with is that would require inversion is something like an 11 by 11 matrix for the reproduction and matrix used to estimate a single camera. It minimizes the same cost function as bundle adjustment. So bundle adjustment officially is the previous one where you do it all together, but this minimizes the same cost function as bundle adjustment, so it should get you to the same point, assuming that there's a unique minimum, and there can be several, but it may take longer to converge is the only thing with that. But nonetheless, so by longer to converge, I don't necessarily mean more calculations. It's just that it mightn't go in the right direction in trying to get to the result. Okay. Sparse methods, we won't go into detail on these as they require advanced linear algebra and looking at the block structure of matrices, which you've seen a little bit about the block structure of matrices in previous things where we can look at blocks separately, but I'm not going to go into it here. While these are considered very difficult to implement as algorithms, there are cookbook style algorithms that can be followed, and the appendix 6.3 of the Hartley and Zisserman book can explain those in detail if you ever find yourself wanting to go through them. So those are methods for dealing with dimensionality. What I'm now going to just quite quickly go through is some methods for solving nonlinear problems. So how we get to the bottom of some difficult function that we want to deal with. And I'm only going to mention them here briefly because these are methods that I will go into in a lot more detail. Well, certainly the gradient descent method. I'll go into in a lot more detail when it comes to the machine learning and to kind of deep learning subject that we're going to do next semester, which hopefully most of you will be back for. How many of you have come across this term gradient descent? Yeah, in neural networks, and that's where we'll be covering them later on as well. But it's a much more general algorithm that we can use for finding the minimum of a function. It's just particularly useful in neural networks, which is where they've appeared before. And we'll do much more of that as well. Yeah, so in the differentiation is certainly part of it, as you can see it here. For our gradient. So gradient descent is what we call a first order method in that we use first derivatives only. And it aims to find the minimum of a function. So remember that the minimum of a function is generally a place, if we've some function here, it's generally a place where the gradient is going to be 0. Okay. The problem with that is that we can have several places where the gradient is 0, and we're always trying to find. That's not going to let me do that. We're always trying to find the one that's the smallest. Okay, so the one that's the lowest down. So as you can see here, I've found one here, but this is continuing to go here. So does it go on forever, or does it level out and continue to go up the way? And is there a smaller minimum? That's always a problem that we're trying to solve. Now the formula for it here is given that what we want to do is we want to try and find the right parameters. So I'm just given the parameter here as x. Now bear in mind that I'm going to show you a one-dimensional version, but what we would solve in terms of these examples here, this could be a 115-dimensional problem, okay, or much higher than that again. And when we get into neural networks, you could be dealing with hundreds of thousands of dimensions, okay. The same idea applies. It just becomes a much more complex problem to solve. But what I'm going to do is show it to you here as a one-dimensional problem, just so that you can get the sense of what's going on. So, sorry, what I'm going to do here, I'm just going to copy my formula here so that we have it on the next slide. Alpha here is called the learning rate, and I'll explain what that is in a moment. Okay, so that's there. So what I'm going to do is I'm just going to draw a graph here, some description here. Okay. I'm getting very nervous, guys. We're getting to that time where I should have a crash in my Panopto system, and it hasn't happened yet. So there's no doubt it's going to happen any minute now. All right. So let's imagine that we have some form of a function here, just going down in this direction here. Actually, sorry. What I'll do is I'll draw a slightly different one for this. Okay. Okay. So this is our function, and the minimum of it is down here, and we want to try and find that. Now what we have here is we have x on the x-axis where it should be, and this is what you'd normally call y, but we're going to call it the function of x. So whatever value of x, that gives us some value in the function. Okay. Now let's imagine that we start at some point here. Okay, so we have some value x that we start at. So we're just going to call that xt for some position that we're starting at. Now what happens here is that we look at the gradient around us, and we see that the gradient is maybe going in this direction here. Now gradient is normally given as positive. So you have the idea of the rise over run. So we would assume that the gradient is going up in this direction here. The thing is, we want to go down. Okay, so you can very much think of this, and sometimes it's described as this is like a blind hill walker. Okay, which is a dangerous thing to do. But anyway, a blind hill walker, and they're up on a hill, and they want to try and find the bottom. They want to try and find the bottom of the valley. So what do? They take a quick feel around with their foot. Okay, I'm doing this with my foot at the moment. I don't know why, because you can't see it. Okay, so you just have to imagine this is happening down below, right? See, if they feel around with their foot, and they find which is the direction that's going down. And what they decide to do is they decide to say, well, okay, I'm going to go a certain amount in that direction, and then I'm going to make a further decision. Okay, so how far do they travel in that direction before they next take their measurement is the question. So how big a step do they take? Now, of course, a hill walker is going to be governed. How big a step they take is governed by how long their leg is. But in our case, we're not bound by that. We can take any size of step we want. What's going to happen here with this is that we have our step size, which is alpha t, which we make a decision on. We decide how big we want that to be. But we also have the size of the gradient. Now, a lot of people think, well, the gradient goes in that direction or it goes in that direction. But in terms of our x, we can only move this way or this way. And that's all we're going to do. So because our gradient is normally given as a positive number, we have a little minus here to tell us go in the opposite direction because we want to go down. Okay. So what we do is we make a decision about what our step size is going to be. Now, the steeper that gradient is, so the steeper the gradient is, multiplied by whatever our step size is, the bigger the move that we make. Okay. So there's two things here. If we have a big step size, then we're probably going to make a big jump. If we have a big gradient, then we're probably going to have a big jump. But bear in mind, if the two of them are big, we're going to have a very big jump. And if one of them is small and the other is big, we're going to have somewhere in between. If the two of them are small, we're going to have a very small move. Really, the only thing, we can't govern the gradient. And the point is that we would expect in most of our problems, like let's say in the problem that we're trying to solve tonight, we would expect that if we're a long way off, then our error is big. And where we're supposed to be is a long way off, and that therefore our gradient will be big. So we should be taking big step sizes in that direction. Okay, so that's fine. And as we get closer and closer, our error gets smaller, and therefore our derivative gets smaller, and therefore we would take smaller steps at that point. So what happens is we take some step in that direction. Let's say, okay, so I decide I'm going to move this far in that direction. This would be xt plus 1. And what we do is we measure what our point is there, we find out what's our gradient at that point, and we go and make another move. So we move again in this direction here by some amount governed by the two pieces of information. That gets us to there. Maybe take a different color here. We measure the gradient again. Once again, that maybe moves us to here. Okay, and now we've got a different gradient, okay, which is much smaller. So we're going to take a smaller move because of that. So by xt, we're not -1 in terms of a distance. I just mean that we're in the next step. Okay, so our next position in terms of it. Okay, so that's all I mean by that. Yep. Yeah. So that's an index. It's not it's not our actual position on the thing. Because we've no guarantee it wouldn't go in the other direction either. So we get here and we do a smaller step, so that gets us to there. And again, we're almost level here, so we're doing smaller steps. And what we're going to find is that smaller and smaller and smaller steps until we eventually get to that, and we won't go up. What can happen though is if we have an alpha that's too big, what this might do is when we're here, it might say, okay, make a jump to there. And now we get to there, and all of a sudden we're going back the way. And we take too big of a jump and we jump to here. And now we're going back the way again. And so what you get is this situation where you're jumping around in the bottom of this bowl and you can't find the bottom of it very well. Okay, so that's the problem with having a big one of those. So everybody thinks, well, let's set it small. But the problem with small is it's going to take us forever to get our hill walker down to the bottom of the thing. And of course, we don't know much about this. So there's people spend lots of time researching what is the ideal step size to have. Can we change our step size as we go? As we see circumstances arise, should we change our step size? And of course you can. So there's lots of different things, and we can also decide to change our step size depending on how big our gradient is. So we can make decisions on all of those things. We get into that's getting into a lot more detail to do with optimization, and there's plenty of papers to read on that. But that's the idea. So that's gradient descent, and it's trying to find the bottom of the function. So that's one mechanism for doing this. The other one is called Newton iteration, or Newton's method, which you may have come across. I know you may have done this in maths at some point, Newton's method. So this is a method for finding the zeros of a function, i.e. where a function is a value of 0. For optimization, we use the Newton method to find where a function has a derivative of 0 and so is at its minimum. Now, Newton's method is a second order method, or at least it's a second order method when we're dealing with optimization. I'll explain that in a moment, but it means that it uses second derivatives as well as first derivatives. Okay. So I'm just waiting. Vin has been typing here. What if, as you were suggesting, if there are two valleys, right? You're getting into a whole module there of problems to try and solve there, Vin. So if there are two valleys, you have what's called a kind of a non-convex problem. And so the situation that can occur, and this happens with the same with the other method as well. So we have something like this. Let's say we go down and then we go back, and we have another one here and something like that. Okay. And the trouble is, if we start here and we come down here and we find the bottom of that, are we ever going to move out of there? Are we ever going to find that this is actually the global minimum? And no, we're not. There are loads of different methods that say, well, if we think that we're not near the bottom for some reason, we can do this kind of what they call simulated annealing. It's where you kind of throw everything up and kind of start it again, hoping to find another spot. So it's a little bit like one of those puzzles where you're trying to get all the little balls to fall into something. There are those sort of methods. Within machine learning, it's a major problem finding these local minimum if they're not good local minimum. But what we also find is that in many of these very, very complex functions, the local minimums tend to be, because remember they're in very high dimensions and all over the place, they tend to be generally as good as you're going to get. So there may of course be some better global minimum somewhere, but it may not be worth the effort to try and find that versus the local minimum that you get. Okay, but if it sounds like I don't have a perfect answer to your question, Vin, it's because nobody yet has a perfect answer to that question. It's a really, really tough nut to crack. So firstly, the Newton's iteration in its original form is to try and find the zeros of a function. So where a function crosses 0. What we then try and do is use it for optimization, and we get the derivative of it, and we want to find where is the derivative 0. And remember, if we get the derivative of a function, that is a function in itself. Okay, so let's firstly describe the idea of finding the zeros. So let's imagine we have some function here and here. Vin is the question. I was thinking the profile would be like Gaussian most of the time. You're saying that the function, is that what you mean? The function would be Gaussian? No, not in terms of that. Now I know the fact that we said that the noise is Gaussian, but that doesn't necessarily mean that the surface would look Gaussian, because remember Gaussian is something that goes up like that and down like that, so it doesn't really relate to where our minimum would be. So that would not be. Don't make any assumptions of that particular type. Okay, so going back to this idea here. Firstly, in this case, we're not doing the optimization problem. We just want to find where's this 0 point, and then that's going to lead us on to how we can use it for the optimization, right? So the first thing is what we have here at this point is called f of xt. Okay, so it's what is the function when we're at position xt. Okay, so that's there. Okay, and we get the derivative here. I'll just draw a straight line here down to there. Okay, so what we have now is that this point here is our guess, our first guess as to where the 0 crossing will be, and this is what we're going to call x t plus 1. Okay, x of t plus 1, which is going to be our next position. And what we're going to do when we get there is we're going to do another derivative. And of course this derivative here, if I was to draw it, goes out in this direction here. Okay, so it hits there somewhere. I'm not sure where my function was going there, so let's imagine it's there. So what happens is then we can go down to that. So you can go either side of this. We'll once again then draw back in this direction to there, and that'll get us this position here, and then we draw in that direction there. And as you can see, with each one we're getting closer and closer to that 0 point. So when they match, we know we've found it. Okay, so the question then is, okay, that's fine, that idea, but how does this match to our formula as we have it there? Okay, so let's have a think about that. So firstly, our distance there, our height there, is equal to f of xt. That's its very nature. That's where it is on our map over here. Okay, on our y-axis. So that's the first thing. The second thing is, what's the distance between here and here? Well, that is xt minus x of t plus 1. Okay, so that's the distance between those two there. So how do we figure out what our gradient is here? Because remember, our gradient is written as f prime. Are you used to that notation, that f prime idea, by the way, that I put there? Are you used to that notation? You've seen that before for meaning derivative. So that just means dy dx, okay? You're familiar with that. Okay, so yeah, because it's a much more shorthand matter. Is it American? I have no idea, Maurice, whether it just comes from somewhere else or not. I'm not sure. But it's certainly a much more shorthand way of writing it when you're writing larger formulas. So I don't know. So this is f of x what do we find? We're looking for f of x t. Okay, so okay, very good. Maybe that's where it comes from. Okay, so what we're trying to do is we're trying to find the derivative, and what we would say is that the derivative is equal to these two numbers, the rise over the run here. Okay, so what we would do is we would put the f of x t, okay, so its position, over the xt minus xt plus 1 is how we would write that. Now all we need to do is now manipulate this function around a little bit. So I can bring these guys over to this side of the equals, and I can say x of t minus xt plus 1. So in the previous case it's divided in, it's just multiplied on this side, and that's multiplied by f prime xt. So forgive me, I should really be jumping steps here at this level, but just to make sure that you all follow. And then, of course, what I can do is, because that's multiplied on that side, I can just drag that down there, and it's divided on this side. Okay. And then what we have is, we want to find out what's xt plus 1, which, of course, is a minus in front of it. So we say that it's equal to minus xt. And then I'll just want to move this out of my way here. Move it down there. Minus xt, and then plus this f of xt over f prime of xt. Okay, and of course we can just get rid of that minus. That becomes a plus, and this one here becomes a minus. Okay, and that is what we have on this side of the sheet here. Okay, so that's where that idea comes from, and it basically says that if you just update it, you can keep going. Okay, now what this means for our optimization problem, because it's no good for us to just find where it crosses 0. What we want to know is where is its derivative 0. So all we have to do is just get the derivative of all of this, and that would get us to get us the derivative of all the functions, and that would get us to it. So basically all that means is that we can change our xt plus 1 xt minus f xt over f prime xt, and we just get the derivative of that and get the derivative of that, and that means that we're now going to find where our derivative function goes to 0. Okay, so I could do that by trying to redraw this as the derivative of the function all the way along, but of course I don't really know what it looks like and so on, so I'm not going to do that. But I'm just going to show you one last thing, which is a kind of a mechanism for doing this. I'll try and copy as much of this as I can, and then get rid of some of it. So you can think about it in that way, that in other words we just get the derivative of this function here, and then find where it crosses 0, and that's a perfectly good way to think about it. But one other way to think about it is that what we actually do is we at each of our points here, at our starting point, what we do is we get a parabola, okay, like that, and we try and get that to match as closely to our point. Okay, to match as closely to our function, and we find the 0 of that. Where is that? And that gives us our point there. So what we then do is we try and find a parabola that fits that, which is probably going to find you one that goes something along the lines of that try and fits the function there. It's going to find you some other 0 point, and you work your way from that down slowly until you find where is the bottom of the thing. Because remember, the bottom of the thing is not going to be here. It's going to be wherever this thing levels out. Okay. So it's always just using different parabola sizes to try and find where the bottom of your function is. Okay, that's another way to look at it. It's maybe not the best way to look at it. It may be better to think about this as just the derivatives of it. But that's the idea of what we're doing. Now, there are a few problems associated with that just to be aware of, right? And one of them is that if I was to be in the wrong starting position, let's say I was up here, there's a perfectly good parabola that's going to fit that, and it's going in completely the wrong direction. And we're going to find where its derivative is 0, so we're going to find out a maximum of the function rather than a minimum. That's something that doesn't happen in gradient descent, because gradient descent always tries to descend and always tries to get down to the bottom. But of course it can happen with Newton's method. So Newton's method is normally a good bit quicker if you start from a good point. But if you start from a bad point, you can be in trouble. Okay, so oftentimes what will happen is that you will start with maybe gradient descent until you can get to some point, and then you would move on to Newton's method. But in most cases, in things like neural networks, which are extremely high dimensional, extremely complex functions, what you'd be trying to do is you'd be trying to fit, you know, a parabola that's in 100,000 dimensions into some bowl somewhere. It's not necessarily going to be the best way to try and solve the problem. And so in many cases, they just stick with gradient descent and loads of different iterations of that algorithm that can work. Because the other thing you have when you get into neural networks is that we don't know the full function. We only have some data from the function, and at any given time we only get a small little bit of data. So in actual fact, our view of the function is constantly changing. We call it stochastic, and therefore we use an idea called stochastic gradient descent, which is that you're descending this gradient, bearing in mind that your function is constantly changing underneath you, but hopefully not by too much, hopefully still in line with what you're doing, and that finds you the problem. But you do find that it's hopping up and down all the time when you do that. So we'll, as I say, we'll discuss that much more when we get into machine learning. I'm not going to probably do much more on the Newton's method, but the stochastic gradient descent and its variance, stochastic gradient descent, and all the different optimization algorithms for them, we'll be discussing that lots when we get to that module. Okay, so that's it for tonight and for the standard lectures that we're going to be covering. As I said, we will have a guest lecture after Easter, but this is the last of the lectures. So thanks very much for your attention all the way through the module. I hope you've enjoyed it. I hope you've been challenged by it, and I think everybody has. That's important. Obviously, you're not going to learn anything unless you're challenged in some way. But I hope you've got some enjoyment out of it. Okay. That's no problem, guys. And just a reminder to do get working on those sample exam questions and putting your responses up. I know you're working on your other thing. I know you're working on the other project as well, but don't leave the questions until the last minute when I can't give you assistance with them. So make sure that you're trying to do a little bit of all of those things, so that you don't end up with one thing being left to the end. Okay. So I'll say goodnight to you at that, and I will chat to you after Easter. I will be available to some extent over the Easter period if you're sending emails, because I'll be working away here. But you just mightn't get quite as quick a response. Hope you enjoy the break, but I also hope that you get plenty done during it when you're done with the lectures. Okay, so good night, guys.